Hello, Algebra 2. So today we're going to be starting examples 3 through 5. We're going to be looking at examples 3 through 5 in lesson 6-7. So I'm on the bottom of page 454. The first thing I want you to do is to copy down these steps for graphing a polynomial function. So if you haven't done that, please pause this video. And again, I want you to write these steps down. So steps for graphing a polynomial function. Now that you've studied factoring, solving polynomial equations, and end behavior, you can graph any polynomial function. So you guys learned how to graph quadratic functions, right? You find the axis of symmetry. We did that in class, remember, on the board in the back. So you find the axis of symmetry, you find the vertex, you find the y-intercept, you find two other points, right? And then you plot it and then reflect the points over the axis of symmetry, and it forms a parabola, which is for a quadratic function, right? Now we're going to learn how to graph for any polynomial function. So step 1 here says find the real zeros and y-intercept of the function, plot the x and y-intercepts. Make a table for several x values that lie between the real zeros. Plot the points from your table. Determine the end behavior of the graph. Sketch the graph. It's actually a lot more easier than it sounds. Okay, so now we're going to start with example 3. Okay, example 3 says graph the function. So we have f of x equals x to the third, f of x equals x to the third, or x cubed, plus 3x squared minus 6x minus 8. So step 1 that you just wrote down says to find the real zeros and y-intercept of the function. So the first thing we're going to do is identify the possible rational roots by using the rational root theorem. So that's when you take p, right, which is the factors of -8, over q, which is the factors of 1. So when we do that, we end up with plus or minus 1, 2, 4, and 8, right? All you did, because it's over 1, because a here is 1, or q is 1, you're just listing the factors of -8 here. So these are our possible solutions, our rational solutions, okay, for our rational roots, real solutions for rational roots. So step 2, we're now going to test possible rational zeros until a zero is identified. So we're going to test x equals 1 and x equals -1 using synthetic division. When I do that, okay, x for 1 has a remainder of -10, okay, so that doesn't work. However, when we test -1, we see that we have a 0 here. So, therefore, -1 is the solution. So now we're going to factor step 3. Okay, when you do this out, you end up with zeros of -1, +2, and -4. So once you find your zeros, right, you factor. So f of x equals x plus 1 times x minus 2 times x plus 4. So then our end zeros, right, our zeros are -1, 2, and -4. So we're going to plot those, right? You're going to have a coordinate plane over here that you're going to be plotting these on. So I plot -4, sorry. I plot -1, and I plot 2. See it? Those are my 3 zeros that I found. Okay, step 4 says plot other points as guidelines. So we're just going to pick points in between these, you guys. All right, so they pick 0. All right, and when you substitute 0 in for x up here, you solve and you get -8. So that actually ends up being my y-intercept down here. So I plot 0, -8, that's my y-intercept. So now I have this point, down here, up here. Okay, then you're going to plot points between the zeros. So the book chooses -3 and 1, okay, because -3 lies in between -4 and -1. And then from there you have between -1 and 2, you have +1. All right, so they pick -3 and 1. So when you plug -3 in for x, what do you get? You get 10. And then when you plug 1 in for x, what do you get? Your output, right, is going to be -10. So when I substitute 1 up here, I end up with y equals -10. So these are my coordinates, -3, 10, and 1, -10. You're going to plot those points. Okay? Then your last step now is to identify the end behavior. So when I look back up here, my degree is odd, right? My degree is odd and my leading coefficient is positive. All right, so when I come over to my chart over here, okay, my leading coefficient is positive, so I'm in the first row. And my leading degree is, my degree for my polynomial is odd, so I'm in this box here. So what that means is, as x increases, right, my y increases, and as x decreases, my y decreases. That's what you see over here. okay? Which means as x decreases, y increases, so that means that my final arrow is going to be pointing down. And as x increases to positive infinity, y also increases to positive infinity. So as I go right here, my arrow should be pointing up. So now when I sketch the graph, I'm using all this information. So I start here, okay, I have to get from here to here, but I know that this arrow has to go down. So if this arrow is pointing down, which way do I have to go now? Up, and then around. I come down, and then I'm going to dip back up, because my final arrow needs to be pointing upward to positive infinity. So that's a rough sketch. Guys, I know this isn't easy. You're welcome to use a graphing calculator to check your work, okay? This part here gets tricky. To be honest, I want you to understand these steps, but I will allow you to use a graphing calculator in order to plot these. Okay? If you want to try, check it out 3a and 3b on your own. Here are the graphs. This is what the end graph would look like. So if you put this into your calculator, your graphing calculators, and hit graph, this is what you should see. Okay? And again, step 5 here, I just put use page 453 chart, which is the end behavior chart, okay, in order to determine this. Alright, so now we're going to move on to a turning point. So what is a turning point? A turning point is where a graph changes from increasing to decreasing, or from decreasing to increasing. A turning point corresponds to a local maximum or minimum. So if I look back up at this graph here, right, I have a turning point here. See how we're from left to right, right? We start up here, we're increasing, and now we turn, and now we decrease. And then we have another turning point where we were decreasing, but now we're going to increase again. So I have two turning points here. See it? For a function f of x, f of a is a local maximum if there is an interval around such that f of x is less than f of a for every x value in the interval except a. For a function f of x, f of a is a local minimum if there's an interval around as such that f of x is greater than f of a for every x value in the interval except a. Alright, that sounded like a bunch of gibberish. So, let's just look below it. It says a polynomial function of degree n has at most n minus 1 turning points, and at most n x intercepts. If the function has n distinct real roots, then it has exactly n minus 1 turning points and exactly n x intercepts. You can use a graphing calculator to graph and estimate maximum and minimum values. So I really wish we were in class together, you guys. My graphing calculator is in my desk right now. So I can do this with you, but it's not hard. You just go to graphing, and you enter in your function here. So it's going to say y equals, and you'd put x to the third minus 2x squared minus 5x plus 6. Then you'd hit graph. And this is what you should get. So play around with your graphs, you guys. Try these two examples out on your graphing calculator, and you should get graphs that look like this. Okay. So last up we have example 4. Okay. So example 4 says determine maxima and minima with a calculator. So here we're going to graph g of x equals 2x to the third minus 12x plus 6 on a calculator, then estimate the local max and min. So when you graph this on a calculator, you guys, this is what you're going to see. Something similar to this. Alright, so when I look at this, the graph appears to have one local maximum and one local minimum. See it? This is the max, so if I come up, now I have a maximum turning point and then a minimum turning point. That's called a maxima and a minima. Alright, so step 2 now we're going to find the maximum. So if you press second and then trace on your calculator, right, you access the calc menu, then you're going to choose 4 and then maximum. And this tells you guys the local maximum. So the local maximum is approximately 17.3137. That's this point here. The local minimum, you press second trace on your calculator to access the calc menu. And then you're going to choose 3 for minimum, and that will give you the minimum. The local minimum is approximately negative 5.3137. You would never be able to tell that just by looking at this graph, you guys, because it's so small, okay? But that's the max and that's the min. Again, you can do all of this on your calculator. What I want you to note is that maxima is the plural form of maximum. That just means that you can have more than one. And then the minima is the plural form of minimum. Okay, so here we only have one maximum, so it's just called maximum. But if I had more than one, say I had up, down, I had 2 ups, right? 2 turning points, 2 max turning points, that would be called maxima. If I had two minimum points, two minimum turning points, that would be called minima. So again, I suggest you guys just play around with your calculators and try this out on your own, okay? If you try 4a and 4b, this is what you should get on your calculator here and here. And here, using these steps 1, 2, and 3, the minimum is negative 4.0887, and the max is negative 1.9113. And then same here, 4b. 4b just has a minimum, apparently, of negative 6. Okay, that means if they hit maximum here, it would just be blank. There is no maximum, which means there's no max turning point for this graph. When I look down here, you can see that, all right? This is a parabola, so there's just a minimum. See it? Because there's a minimum, right, there's just negative 6 for a min. There is no maximum turning point here. And then example 5, I'm not going to have you guys be held responsible for this, okay, but you can read through this on your own. It's just a real-world application problem, so you can read that and try it out. I know we just covered a lot, so feel free to watch this video again. I think the book actually does a really good job of explaining all of this, so take the time and read through step 1, step 2, step 3. When you do the homework, you guys, refer back to these examples. So if you're doing a problem from example 4, okay, it tells you in the book, right, when you look over here, it says see example 1, 2, 3, 4. So if I'm doing a problem from example 4 and you're having trouble, come back here and mimic these steps. It tells you exactly what to do. All right, so please utilize that. One other thing I wanted to show you, if you're having trouble, the book has a website. Okay, so you can go to go.hrw.com. Okay, and then you can type in the keyword MB767. So that will take you to these examples here, and there will actually be videos on each of these examples, and it'll help walk you through these examples if you're having trouble. So it's kind of like having a teacher right there with you. Okay, so I highly, highly recommend you use this, you guys, when you're doing your practice problems. All right, so you guys are doing a great job. Keep up the good work. Bye. Oh, I should probably shut it off. Here we go.